Hello everyone. So in this pre-lecture tutorial, we're going to build upon what we learned in the last pre-lecture tutorial. If you remember, in the last pre-lecture tutorial, we were just working on piecing together rate laws for a chemical reaction. So for a generic reaction such as this, where I have some reactant A going to some set of products, remember that we said that we can write a rate law that can be considered representative of the change of reactant concentration A with time, and that rate law has the form of some rate constant K multiplied by the reactant concentration, again provided that I have first order kinetics. Now, this type of rate law, which is actually called a differential rate law since it expresses a change in concentration versus a change in time. This is useful for seeing the effect of concentration on rate, since concentration is explicitly stated in the mathematical expression all the way over here on the right. However, if I wanted to explore the relationship of time and how it affects the rate, well, that's going to prove a little bit more challenging since my time variable is sort of locked away in this differential term. I need an explicit expression of time, t, without this time interval. I need a specific time. And so in order for me to do that, basically it involves a little rearrangement and a little bit of calculus. Specifically, I need to integrate this rate law equation. Now, if you are not taking calculus, don't panic. If you are taking calculus and you haven't studied integration yet, that's fine. Don't panic. Basically, I'm not expecting you to actually work the calculus to show me how the differential rate law becomes the integrated rate law. You just have to be able to use the integrated rate law and also understand how it can be useful to chemists. And so if you take a look at the AP data packet, that's also clearly indicated because they actually give you the integrated rate laws in the kinetics section of the data packet. This first equation is actually the integrated rate law for first order reaction kinetics. The second equation is the integrated rate law for second order kinetics. And this last equation is actually the half-life for first order reaction kinetics, which we're going to actually discuss in greater detail in class tomorrow. But essentially, you're going to be expected to algebraically solve these equations, which I don't believe will be a challenge to any of you. But you also have to be able to use these equations as diagnostics. So let's go back to the tutorial and I'll explain what I mean. As I was showing you before, for a first order reaction equation, basically the integrated rate law would be the natural log of the concentration of A at time t. That's equal to negative kt plus natural log of A at time 0. So again, A at time 0 is your initial concentration. A at time t is exactly what it sounds like. It's your concentration of A at time t. T is the time itself. And K is our rate constant. Now, if you think back to linear algebra and the equation for a straight line, other than just being another equation that we can solve, basically this equation, this integrated rate law for first order kinetics, is telling me that if I plot the natural log of A versus time, so natural log of A is my y variable, time is my x variable, that'll get a straight line. And this straight line will have a slope that is equal to the rate constant multiplied by -1, or negative k, and my y-intercept will actually be the natural log of my initial concentration. And so what that means is, if for any reaction I'm given a series of concentrations that are measured at specific time intervals, if I take the natural log of those concentrations and plot them against time, I'm going to get a straight line. And the slope would actually be the rate constant times -1. Notice if I plot the concentration versus time by itself, I don't get a straight line, I get a curve. If I plot the reciprocal versus time, I still get a curve. And so the only way I'd get a straight line is if I actually plot the natural log of A versus time. So that gives me a diagnostic test to determine whether or not a reaction is first order or second order. Now, the other rate law that you saw in the EP data packet, once again, for the generic reaction where we have some reactant A decomposing into a set of products, again, based on what we learned last week, that rate, which can be considered the rate of disappearance of reactant A versus time, if I have second order kinetics, that's some rate constant A times the concentration of A squared. Again, rearranging and doing the calculus, we saw in the EP data packet that basically the equation you get is 1 over A at some time is equal to KT plus, not the natural log, 1 over the initial concentration. So once again, comparing this to our equation for a straight line, what this is showing me is if I plot 1 over the reactant concentration as a function of time, if I have second order behavior, then that plot is going to give me a straight line. And that straight line will have a slope of K itself, the rate constant, and a y-intercept of 1 over the initial concentration. So basically now, if I try and do what I did for first order behavior, if I try to plot the natural log of A versus time for a reaction that is second order, then basically I no longer get a straight line, I get a curve. Notice I still get a curve if I plot the reactant concentration itself versus time. But this time, if I have second order behavior, if I plot the reciprocal of the concentration versus time, now I get a straight line. And that straight line would have a slope that is equivalent to the rate constant. Now, one case that we haven't talked about, and it actually doesn't even appear in your data packet, but we haven't discussed what happens when we have zero order reaction kinetics. So again, for a reaction where I have some reactant A falling apart to some set of products, once again I can write a rate law that can be considered the rate of disappearance of reactant A with time. And this time, if it's zero order, that means that the rate is constant. Essentially, there is no concentration term because it's the concentration of A to the 0, and anything raised to the 0 power is 1. If I go ahead and rearrange and do the calculus, basically what you're going to get this time is actually a somewhat simpler equation. I'm going to get the concentration of reactant A at time t that's equal to negative KT plus the initial concentration. Where again, if I do this comparison to the equation for a straight line, that means if I have zero order reaction behavior, if I plot the concentration this time against the time itself, then I'm going to get a straight line. And that straight line is going to have a slope that is -1 times the rate constant. And I'm going to have a y-intercept that is equal to the initial concentration of the reactant. Looking at my graphs themselves, notice that this time, if I plot concentration versus time directly, now I do get a straight line, again having that slope of -1 times the rate constant. Whereas if I try to plot the data for a zero order reaction as if it were a first order reaction or a second order reaction, notice that we get curves instead. So that's really one of the main ways that chemists tend to use this sort of integrated rate law approach. It is useful for calculating the time over which a reaction takes place. It's used for calculating a concentration at a specific time if I know the initial concentration and the time the reaction's been proceeding. And so that's the algebraic application, but it's very useful as a diagnostic tool to know what order of reaction we have in front of us. And so an example of that is this example problem that I've actually placed on this slide for the tutorial. Suppose that I have a reaction that's summarized by the following chemical equation. Now, suppose that I was initially given this data right here. All right, notice it's concentration versus time that's been measured at 10-minute intervals. Now, they want me to determine the rate law, and they want me to calculate the rate constant. Well, if I try to look at these specific intervals, I'll call these intervals M1, M2, and M3. Well, if I take a look at that for the concentration data itself, so basically I'm going to calculate the change in the concentration, so I'll take the difference between these two numbers and divide by the time interval. Okay, if I do that for M1, M2, and M3, I actually get values of negative 1.49 times 10 to the negative 4 and negative 1 times 10 to the negative 4 and negative 6.7 times 10 to the negative 5. Notice that these numbers are changing. Each of these values would represent slopes, and the slope is not constant. And so basically that means this is not linear. And so since A versus T is not linear, then we know for sure that it's not a reaction that's zeroth order with respect to the reactant concentration. And so if I were to do that, then my next step should be to evaluate the natural log of each of these concentration values, and also the reciprocal of each. So that this way I can test out the first order possibility and also the second order possibility for this particular reaction. And I'm going to do the same thing. I'm going to pair up all of these different values, and I'm going to calculate, in the case of the second order reaction, so for the data that is the reciprocal of the concentration, I'm going to calculate the change in 1 over A versus time. So that means I'm going to subtract these two numbers and divide by this same time interval. And so if I do that for each of my three chosen intervals, for M1, M2, and M3, what I get is 2.69, 4, and 5.97. Once again, notice that these three values, which would correspond to slopes on a plot of 1 over A versus T, basically these slopes are not consistent either. And for a line, the slope must be consistent. So that means that this plot would also not be linear, which means that this reaction is not second order either. But if I do this same analysis for the natural log of A data, and if I calculate what would be the slope, meaning I'm going to take the difference between the natural log of the reactant concentration as a function of time, so that means I'm going to subtract these numbers from each other, divide by that time interval, and so on for each of these intervals in the boxes that I've drawn, then basically what happens is for M1, M2, and M3, I actually end up with the same value this time. It ends up being negative 2 times 10 to the negative 2 each time. And so in this case, I get a constant slope, which means that this graph would be linear, which means that the reaction is first order. So if I had to write the rate law, that would be rate is equal to K times A. Now, they also asked me to calculate the rate constant. Well, in this case, I don't necessarily have to do a calculation. If you recall, for first order reaction kinetics, if I calculate the slope of the line that I get when I actually plot natural log of a versus time, then I'm going to get -1 times the rate constant. Well, here is that slope for this particular graph. And so that would mean that my slope is equal to -k, or in this case, my rate constant would then have to be 2.00 times 10 to the -2. And again, since natural log terms are unitless, and the time scale here is in minutes, then that means that this particular rate constant would actually be expressed in units of inverse minutes. So try working on the follow-up assignment. Use this example that I've given you as a template. Use your examples in your textbook for this particular section. If you have any questions, email. We'll be discussing this further in class, and I'll see you guys then.